So today we are actually happy, to share some of our insights into a very important and evolving topic in communication technology. So which is the non-terrestrial network, or in short, NTN. So basically, in this session, we will walk you through the fundamentals and the key challenges surrounding NTN. And also we will introduce Unrich's products, so which basically enables in providing solutions for testing and also for validating NTN devices. So having said this, let us start with this session and see why NTN has become such an important concept, not just for the current communication technology, but also the future wireless communication technologies. So in today's session, we will begin with a quick introduction to NTN, and next we will look at the different types of satellites which are considered as the candidate for NTN deployment. And then we'll also explore architecture of NTN, and we'll also discuss some of the major challenges which are faced during the NTN deployments. And finally, we will highlight Unrich's solutions and products, so which help in testing and validation of the NTN devices. So let's get started. So what is NTN? So NTN is basically a 3GPP defined radio access, so which basically uses aerial platforms. So these aerial platforms, they can include satellites, high altitude platform systems, or unmanned aerial vehicles like the drones. So this basically, NTN basically helps to extend the wireless connectivity beyond what the existing terrestrial networks could provide. So why NTN matters? Basically, NTN helps to fill the gaps in coverage. So NTN helps to extend 5G and the future, the future 6G coverage to places or regions where the existing terrestrial networks, is unable to provide the coverage. So these regions include oceans, skies, polar regions, and areas which are frequently hit by disasters. So NTN also helps to eliminate, the need for heavy investment, and also it also drastically reduces the time effort which is required in rolling out of the physical base station towers. So especially when we consider the remote and geographical challenging areas, so in such areas, having NTN will avoid such challenges. And then NTN guarantees continuity. So this is achieved by, because NTN can provide an always on link. So this link, which is provided by the NTN, it is exposed to very less disruptions. And the fourth point is that NTN allows for a massive scale deployment and also low power consumption by the devices. So what it means is that NTN basically can support billions of low complexity devices such as IoT and machine type communication devices. So this is possible because NTN, it can deliver a very wide area coverage. And also NTN can support certain mechanisms which basically results in lower power consumptions for these devices. So now let us see how NTN has been integrated into the 3GPP standards. So at first we have release 17. So here both NB-IoT as well as the NR links using the transparent payloads were introduced. And in this release, that is release 17, the main focus was on the frequencies below 6 gigahertz. And next we have the release 18. So here the support for Ka band was added. So Ka band is basically nothing but the FR2 bands. So with this addition of FR2 bands, achieving higher throughput capabilities for NTN deployment was possible. And next we have the release 19, so which is an upcoming release which is targeted for December 2025. So under this release, major enhancements which are expected are the regenerative payloads and the use of Ku band, and also reducing the dependency on the GNSS systems. Now, when we come to the service classes which are supported under the NTN, so today there are basically two key service classes which are supported. So the first one is the NB-IoT NTN, so which is basically designed for low data rate applications. So the typical use cases include transportation and logistic industry, and then we have the energy and agriculture sectors, and also it is deployed in environmental monitoring applications. So the next service is the NR-NTN. So this NR-NTN basically supports higher data rate. So because of this, the NTN services can be used for NR-NTN services can be used for voice, video streaming, and broadband services. This NR-NTN, these are very important, especially when we consider coverage for the remote areas and also public safety communications. Now, when we talk about NTN, so one of the important points that we need to consider is the payload option for the satellites. So there are mainly two types of payload options which has been defined by 3GPP. So the first is the non-regenerative payload option, and the second we have the regenerative payload option. So the non-regenerative payload option, which is also called as transparent payload option or bent pipe payload option. So here the satellite it will act as an analog RF repeater. That is, it will receive the signal from the Earth-based G-Node B and the gateway, and then it simply amplifies this signal and then forwards them to the Earth-based terminal entities. So basically here, the satellite, it does not perform any kind of signal or baseband related processing. So considering this, when you talk about the deployment of this option, so this satellite deployment will be very, faster in terms of time and also cost effective in terms of, budget. So the major drawback with this satellite is that it has a very high dependency on the Earth-based G-Node B or the gateways. So for any baseband or signal processing, it has to depend on the G-Node B, which is stationed on the Earth. So because of this, the total latency of this communication link it is quite high when compared to the regenerative payloads. So when we come to the regenerative payloads, so this is basically targeted for release 19 specifications. So here the satellite is capable of performing the base station functions. So this basically reduces the overall latency in the communication link. So with this option, the connectivity can be still maintained when the feeder link between the payload and the gateway is not existing. So this is possible because the satellite can establish a communication link with the neighboring satellite using the ISL, which is the inter-satellite link. So the neighbor cell will be having a access to the gateway through the feeder link. So this way, through satellite constellation, the link can be still maintained. So now when you talk about the deployment, so this option it comes with higher cost, and also time effort in rolling out of this option is quite high when compared to the non-regenerative payload options. So next, let us look at the candidate satellites which are considered for NTN. So currently, when you talk about the satellite orbits, they are basically categorized into two. So we have the geosynchronous satellites, and then the non-geosynchronous satellites. So geosynchronous satellites, these are basically, they are located at an altitude of around 35,000 kilometers from the Earth's surface. And the orbits of these satellites, they are elliptical and also inclined to the Earth axis. So as you can see here in the figure, the green orbit basically represents the geosynchronous satellite orbit. Under geosynchronous satellite orbit, we have the geostationary Earth orbit, so which has an orbit which is circular, and also it is parallel to the Earth's equator. And when you talk about the speed of these satellites, so these satellites, they have a speed which is equivalent to the Earth's rotational speed. And because of this property, this satellite, they appear to be static or synchronous to the Earth's rotation. Now, when we come to the link characteristics of geosynchronous satellites, so the main challenge here is the large propagation delay. So this is because these satellites are located at a very high altitude, so they are impacted by large delays. But when we come to the Doppler, so the Doppler effect will be zero or negligible because this satellite, they appear to be synchronous or static to the end user. So the non-geosynchronous satellites, or in short NGSO satellites, so this satellite, they have speed which are much higher when compared to the Earth's rotation. So because of this, these satellites, they take around 1.5 hours to 10 hours to complete one revolution around the Earth. So under NGSO, we have low Earth orbit, so which are located at an altitude of 300 to 1,500 kilometers. And then we have the medium Earth orbit, so which lies in the space region between LEO and the GEO orbits. Now, talking about the link characteristics, so compared to GSO, the NGSO satellites, they experience a very large Doppler shift. So this is because they have a very high speed. And when you talk about the delay, so since they are located closer to the Earth's surface, so they have a relatively smaller delay. But this delay will be time varying because the satellites have a very high speed motion. So today, the leading candidates, when we talk about the leading candidates which are driving the NTN deployments, then we have the GEO and LEO satellites. So in GEO, like as I mentioned earlier, since they are static and synchronous, so this link appear to be stable or predictive. So when we talk about the propagation delay, so the propagation delay for geo-based satellite is around 240 milliseconds in one direction. And when you come to the coverage footprint, so the coverage footprint can go up to 3,500 kilometer. So the best suited communication technology for geo-based satellite is NTN, NB-IoT, NTN technology. So this is because, as we all know, NB-IoT applications or use cases, they are very less sensitive to the delays. So the next candidate is LEO. So the LEO link have a delay of around 10 milliseconds in one direction, and the footprint size for the LEO satellites is 1,000 kilometers. So because of this, when we consider any region, for example, here the GEO can cover up to 3,500 kilometer area, but to cover the same region, we will require more number of LEO satellites to be deployed. And the preferred technology is the NR-NTN. This is because of the very low latencies, which is experienced by the LEO links. So next, let us look at the NTN architecture. So in this slide, let us see some of the key components of the NTN architecture. So at the top, we have the 5G core or the 5GC, which performs the standard session management functions, authentication functions, and also user plane functions. And next, we have the NG-Link. So this NG-Link connects the 5G core with the NTN gateway. And then the NTN gateway. So this basically provides the interface between the terrestrial 5G core and the satellite or any aerial platforms. And then we have the feeder link. So these feeder links are a high capacity link, so which basically provides a link between the gateway and the payload. And this feeder link, they use bands such as Ku, Ka, and V bands. So next we have the NTN payload, so which are basically the satellite or high altitude platforms. And then we have the drones or the unmanned aerial vehicles. And finally, between the payload and the users, we have this service link, which is also called as the user link. So these are basically the NR UU air interface. So this provide the direct access between the satellite payload and the UVs. So in this slide, the different architecture options which are defined by the 3GPP are specified. So these are basically categorized based on the two factors. So first we have the NTN terminal entity, whether the serving entity is a UV or a relay node. And then we have the payload option that is employed by this option. So first we have the non-regenerative payload and the regenerative payload. So as you can see here, A1 and A3 architecture, they use a non-regenerative payload. That is, the G node B is located along with the gateway on the Earth. Whereas in A2 and A4, the G node B is located on the satellite. So in this slide, you can see the diagrammatic representation of the architectures. So as I mentioned, A1 and A3, they use the non-regenerative payload option where the G node B is located on the Earth. But in A1 case, the satellite has direct access to the UV, whereas in A3, the satellite will access a relay node and the relay node will have access to the UV. Similarly, in A2 and A4 option, the G node B is co-located with the satellite, that is the regenerative payload option. In A2, the satellite has direct access to the UV, whereas in A4, the satellite will be accessing a relay node and the relay node will access the UV. So now coming to the challenges of NTN. So when we talk about the NTN implementation, so there are several challenges which are faced by both the base station as well as the UV devices. So at first we have this large and rapidly varying propagation delay. So this basically affects the transmission timing in both uplink as well as the downlink directions. And second, we have Doppler shifts, so which basically introduces large frequency offsets in the received carrier frequency. And then we have the issue of discontinuous coverage. So this basically occurs whenever there is a handover between the satellites or the beam switching. Now, to address these challenges, 3GPP has introduced a set of enhancements. So these are applicable to both NR and also for NB-IoT NTN operations. So at first we have introduction of enhanced timing advance, and then we have relaxation of HARC and RACH timings, and then there is extension of RRC and MAC timers. And then we have a frequency precompensation for the mitigation of Doppler shifts. And then we have the efficient feeder link switchover and beam handover mechanisms. And then we also have the satellite ephemeris information, which is broadcasted by the network to the devices. So this basically helps in tracking the satellite's trajectory path. And finally, we have NTN specific spectrum bands, so which are defined by 3GPP so that the NTN operation doesn't interfere with the existing terrestrial networks. So one of the biggest technical challenges when we talk in terms of NTN implementation is the propagation delay. Because these satellites, especially the LEO-based satellites, they keep moving at very high speeds. So the propagation distance between the UV and the satellite, they keep varying. So they keep varying over the time. And because of this varying in the propagation distance, so the propagation delay between this satellite as well as the UV, it will not remain constant. So it will keep changing over the time, and the variation will be in several milliseconds. So as you can see in the figure, when the UV is at the middle of the beam center, so the propagation delay experienced by a LEO-based satellite is around 2 milliseconds. But as the satellite moves over time and the UV, it shifts to the edge of the beams, so the delay will increase and it can go as high as like 7 milliseconds or 10 milliseconds. So now when we look at how this propagation delay will affect the NTN protocols. So at first we have the impact on timing advance command values. So, in order to accommodate for this large delays, 3GPP has, basically extended the range of the timing advance command values. So because of this, the LEO-based satellites, the timing advance command value is expected to cover values around 6.4 milliseconds per direction. Whereas for the geo-based systems, it is expected to cover around 36 milliseconds of delay. So this is enabled by introducing a new IE, which is the TA common R17 IE. This is broadcasted by the, this is informed to the UV through RRC signaling. And next, we have the effect on random access procedures. So basically, in order to mitigate this, impact on the random access procedure, 3GPP has introduced preambles with longer lengths. So this basically ensures that the large delay, it can fall within the correlation window of the patch at the network side. So even when the patch is received at the network with a delay, so it can be still detected within the correlation window. And next we have the early scheduling of the PRACH. So this is basically employed to negate the large propagation delay. So coming to the impact of propagation delay on HARC round trip time. So for LEO-based satellites, the HARC round trip time is expected to be at least 8 milliseconds. And for GEO-based systems, the HARC round trip time is expected to be around 500 milliseconds. Now to handle such large round trip time, 3GPP has extended the HARC process. So it can now support up to 32 HARC process numbers. So the next challenge for NTN implementation is the impact of Doppler effects. So for NGSO, since these satellites, they appear to be static or synchronous to the user, so the Doppler effect will be negligible or zero. Whereas when we talk about LEO satellites, so this can travel at speeds like as high as 27,000 km per hour. So because of this, the carrier frequency is impacted by the Doppler spread. So which basically results in a large frequency error in the carrier frequency. Now coming to the impact of Doppler shift on NR. First, this Doppler shift can impact the demodulation of the OFDM symbols. So this is because the high frequency error, it can lead to the loss of the orthogonality of the OFDM subcarriers. And then we have the frequency error, which is introduced by the Doppler shifts. So this basically impacts the transmission of patch preambles and also the uplink transmissions. And Doppler shift can also cause timing drift. So this will ultimately result in timing misalignment between the transmitter and the receiver. Now to address these concerns, 3GPP has introduced the following mitigation strategies. So at first we have a precompensation of the coarse frequency error. So this precompensation happens by, is performed by both the network as well as the UV. So here the information like the ephemeris information and the GNSS data is used to precompensate the large frequency errors. So as you can see in this figure, because of the precompensation by network and UV, the device which is present at the center of the beam, so they will have almost like ideally it will have no effect of the Doppler shift. But when the beam shifts because of the movement of the satellite, and when the device is at the edge of the beam, so there can be small frequency errors, so which is called as the residual frequencies. So this residual frequency can be corrected by the UV. So for this, the you will be performing continuous estimation of the frequency error, and also it will be performing the phase tracking. So based on this, I mean, for this, it will be basically using the reference signal. So we have the SSB, DMRS, and the CSIRS reference signal, so which will be tracked by the devices to continuously do the frequency estimation. And then we also have the common timing advance broadcast. So which basically ensures that there is no timing misalignment between the network and the UV, and this basically ensures that the reference signals, that is the DMRS, SSB, and the CSIRS, are detected without any distortions in the timings. So now coming to the next biggest challenge, which is mobility management. So especially when we talk about LEO-based satellites, so these satellites, because they are moving at very high speed, and also the beam also they keep shifting on the Earth's surface. So the end devices, which is stationed on the Earth, they will experience frequent handovers or mobility. Now, this handovers, I mean, it can take place between the satellites and also between the beam switching. So this basically requires for very efficient mobility management. So when we look at the challenges for the mobility management, and then we have at first we have the variations in the timing and Doppler shift values. So because of these variations in the timing and the Doppler shift values, the device is expected to constantly adjust their uplink transmission timing, and also they have to constantly correct the frequency offsets. So if this is not performed by the device, then this can lead to radio link failure. So the radio link failure can happen during the handover procedures. And next we have mobility in idle mode. So here there are basically two challenges. So first we have, when the device goes to the idle mode, and then when it tries to come back to the RRC connected state, so device, it may not be in the coverage area of the same cell or the satellite. So this is the first point. So the second point under idle mobility is that the NTN devices, they have to frequently update their location information to the UV. So they have to keep sending this report on the location information. So for this, the UV has to ensure that it wakes up while the device is within the coverage of a satellite. And the third challenge is maintaining a service continuity. So this is very important, especially during mobility when we consider any real-time or critical applications. So now to handle these challenges, 3GPP has introduced the following mechanisms, which includes which includes large beam coverage footprints. Sorry. So yeah, sorry. So this basically includes large beam coverage footprints. So this basically helps in reducing the frequency of handovers. And next we have the predictive mobility techniques. So which basically enables the UV to calculate, the satellite's path, that is the trajectory path of the satellite. So for this, the UV will be depending on the ephemeris information. So with this knowledge, like when the UV is aware of the satellite's path, so the UV can actually predict when the handover can happen in the future. So this basically, it will help the UV to prepare for the handover much before, even before the link starts to get degrading. So next is the extended DRX cycles. So the extended DRX cycles, along with the location-based tracking, it helps the device to wake up only when the device is in the coverage area of a satellite. So this ultimately, it results in conserving the battery power for the device. And then we have mobility management adaptations, which is done at the RRC level. So these are specifically designed for NTN. So this basically ensure the handovers happen smoothly, and also a very stable connection is maintained during the handovers. So here the network will provide information on the satellite's movement, and also coverage time of the beam, and the expected visibility windows of the satellites. So with this information, this basically will allow the UV to initiate the measurements and also the handover procedures. That is for both beam to beam as well as the satellite to satellite handovers. Um, and basically it will reduce the mobility failures because of any radio coverage issues. So another important aspect is the NTN, frequency bands. So for FR1, there are around four bands which has been introduced. So we have the N256, N255, N254, and N252. So these bands, they range between 1.6 gigahertz to 2.5 gigahertz. And the duplexing mode used by these bands are the FDD duplexing mode. So FR2 bands, they are particularly very preferred for applications which require a wide area coverage. And next we have the FR2. So in FR2 we have N512 band, N511 band, and N510 band. So here also the duplexing mode used is the FDD duplexing mode. So the frequency range in uplink is between 27 gigahertz to 30 gigahertz, whereas in downlink, the frequency range is between 17 to 2.2 gigahertz. So FR2 bands, they can support a very high capacity. That is, they can accommodate a very large number of users. But the drawback with FR2 is they are very sensitive to the atmospheric conditions. So similarly for NB IoT, so there are two bands. So we have this 256 band, which basically falls in the S band. And then we have the 255 band, which falls in the L band range. So here also the duplexing mode is FDD. And the frequency range is between 1.5 to 2.2 gigahertz. So coming to the system information blocks, so 3GPP has introduced the system information blocks which are specific to NTN. So for NR-NTN, we have the SIB19. So this SIB19, it provides the required information regarding the serving satellite. So some of the important parameters which I have listed down here are the ephemeris data. So this basically describes the satellite's trajectory or the orbital path. And then we have parameters such as the common timing advance adjustment. So this is basically used for pre-compensation of the large delays. And next we have timing offset, so which are the K offset and the K mac. So this helps in aligning the transmission timing between the UV and the satellite. And SIB19 also provides a validity duration. So this basically will ensure that the UV is aware, like for how long the information which is provided by the SIB19 will be valid or accurate. And lastly, the SIB19 will also include neighboring satellites information. So this will basically help the UV to prepare for satellite handovers and also to track multiple beams of the different satellites. So coming to NB-IoT, so in NB-IoT there are two system information messages. So we have the SIP31 and SIP32. So SIP31 contains the required serving satellite information, so which is similar to the NR-NTN SIP19. So here also in SIP31 we have ephemeris information, and then we have the common timing advance adjustments, K offsets, and KMAC, and a validity durations. So SIP31 is an mandatory SIP. So any cell that is NB-IoT NTN cell which is broadcasting SIP31, so it has to mandatorily send the SIP31. Whereas SIP32 is optional because it includes information about the neighboring satellite. So it is not mandatory; it is just optional. So this is about the fundamental concepts and challenges which are faced in the NTN's deployment. So now my colleague Vidya Sagar will introduce Andritsuit solutions and also products which help in addressing the testing and measurement requirements of the NTN devices. Thank you.
Thank you so much, Bharat. Very good morning all. This is Vidya Sagar. So far we have discussed about the introduction and the architecture of the NTN components. So let us now discuss more on to the what exactly the Andritsu can provide the different platform solutions with respect to the NTN devices. So when coming to that NTN devices testing goals, so basically there are two main challenges in the NTN devices testing. So one is that reference point. The reference point is nothing but if you see this the beam, the green color indicating the beam, if the DUT or any UE will be in the center of the beam, then it is called the reference point. So if the DUT is in place of the beam center, then the satellite can be taking care of the pre-compensated for the delay and the Doppler shift. So whereas the UE is edges of the beam, then it has to be taken care the residual delay and the Doppler shift experienced by the UE can be compensated by the UE itself. So what exactly the Doppler shift? You know that there is a change in the frequency of the received signal due to the motion due to the relative motion of the TX and the RX. So that is a shifting the change in the frequency, that is called the Doppler shift. If you see that the reference point and the beam edge, so the delay has to be compensated from the reference point, which I already discussed by the satellite, and the Doppler shift by the satellite itself. Anyhow, path loss is a time varying non-zero because the path loss is very high. The satellite is located at very high altitude, so the path loss will be it's a non-zero. When come to the beam edge, it should be compensated by the UE itself, whatever the residual delay or the residual Doppler shift has been occurring at the edge of the beam. Next. So let us discuss about more on what the Andritsu can provide the solutions for the different platforms like NTN solutions to the chipset vendors and the module vendors, manufacturers, and also in the like protocol and the RF development. So if you see that when it comes to the platforms for the NB-IoT, so for the protocol testing, we are having the product called MD8430A, so which will be using for for protocol testing for the NB-IoT case. When it comes to the RF testing or RF R&D purpose, we are using the one more product called MT882NC, and also the conformance. You know that if any device before going to the market, it has to be certified for the GCP and PTCR certifications. So even we also provide the solutions related to the protocol conformance and also for the RF conformance. So the product names respectively ME7834NR and ME7873NR. So this is regarding the NB-IoT NTN solutions. When it comes to the NR platform solutions, so for the protocol testing, the product name which we'll be introducing for the protocol testing and RF testing is called the MT8000A. So basically the same product has been used in even for the RF CT and the conformance. The product name is ME7834NR and ME7873 NR. So let us discuss more on the band of frequencies which already we have discussed, which is mentioned by the Bharat. So these are the band of frequencies will be mentioned as per the 3GPP is the region wise. 254 and 255 is focused mainly for the global region, and the 256 band, that is 2170 to 2200 megahertz for the European band. Next. So let us go through the what are the features as per the release 17, the protocol testing in the with respect to NB-IoT NTN, which will be providing by the Andresu. So the product name is MD8430A. So these are the following features currently available with this solution. That is the release 17 NTN and SIP31 already, which I have discussed. This is the mandatory system information which has to be defined for the SIP31 in the NB-IoT NTN, and also different frequency bands, and also the IP based and non-IP based call and MOMT SMSs. These are the available features, and also we can able to simulate different like fixed delay for the time varying delays. Everything can be simulated using this particular product. And also one foremost simulation is like the mobility cases. Example, NTN to NTN, NTN to terrestrial network, the cell mobility and all the roaming scenarios can also be evaluated using this product. So if you see that already we have discussed geo and non-GSO, the time varying, because the propagation delay for the geo satellites is almost it's a negligible. But whereas a non-GSO satellites, it's a time varying as the regions we have already discussed. So the amount of the Doppler shift for the geo cases, we can almost say that zero close to zero, we can negligible. But for the NGOs, it is also the time varying. Next. So next, now we are discussing about the protocol testing solution, that NR-NTN. So in the NR-NTN also has been defined in the 3GPP release 17. So these are the features currently it is available for the NR-NTN, that is SIP19, as we have already discussed. So all the information has to be defined in the system information block. So then that the timing offset, the K offset and MAC offset is also be very important. This feature also be supported using this solution. And hard hack enhancement for the NTN, and also fixed and similar. This is also similar to the NB-IoT case. Even all the mobility cases also supported in MT8000A product. Next. So now we are discussing about that RF solutions for the NTN and NB-IoT. So this is the one product MT8821C will be supporting for the RF related cases. If you see that the 3GPP spec 36.521-4, the release 18 has been supported for the major TRX test cases. TRX is nothing but a transmitter and the receiver cases. So which will be going to discuss more on the each and every test case in the further slides. So what is the Doppler, the propagation delay and the Doppler shift is the time varying in this. So in this MT8821C, we are using the simulate using the AT commands, like the coordinates of the satellite has been defined using the AT command, so that the UE can be demodulate and find out that where exactly the location, the MFRS information has been demodulated by the UE side. So what are the currently bands supported in NB-IoT NTN with respect to RF solution? So we have band 23 and 24 and 253 and 254 and 255 bands. So these are all the bands already we have evaluated with one of our customer. So let us discuss more on the what are the TRX test cases which will be supporting using this MT8821C. Next. So these are the main, supported test case with respect to the 3GPP. So these are called the TX and RX test cases for any DUT in the manufacturer or any chipset vendors or any UE manufacturers or the DUT NTN devices manufacturers. These are very important for each and every when it comes to the TX and RX related. So the TX, why we need to have these kind of verification of the TX and RX characterization measurements? Why? Because in the TX path of any DUT, the major role played by the power amplifier, which can be, giving a lot of interference, or some of the intermodulation products has been generated by the power amplifier, so that it is mandatory to require what is the maximum output power at that antenna it is transmitting from the TX of that particular DUT. So if you see that UE maximum output power, so it has to be specified limit. For example, 23 plus or minus 2 is the tolerance. So beyond that, any DUT or any device should not be transmit, because it has to be interfere with the existing other systems. So that is the one thing. If you discuss about the min power and also the min power, what is the minimum power we can able to transmit in that? So the dynamic range of the TX. So the maximum and the min power of the TX has to be decide the dynamic range of the particular transmit path. And also a lot of because the demodulation quality, because we are using the modulation schemes while transmitting, like QPSK 16 com and 64 com, and also how the modulation, because while transmitting that the modulation, the symbols has been deviated or not, actual from the ideal symbols has been deviated due to that, transmit the vector error. The error vector has been identified. There is a one test case called the error vector magnitude. If you see this error vector magnitude, that is called the EVM. So this is also modulation analysis. The modulation analysis, because the non-linearity of the TX, all these test cases will be verified for the analysis of the non-linearities of the TX path, which is in the NTN devices, or the UE you can call. When it comes to that RX, so RX is very important in any in any UE design. So because the sensitivity, what is the reference sensitivity, is nothing but it is the minimum detectable signal. That means the receiver can be able to capable of handling the very low power, very low powers, so that it can able to demodulate the signal at the low power. That indicates the reference sensitivity level. So it is a very foremost important for the NTN devices, because the sensitivity should be very low. Like for example, generally for the terrestrial networks, the sensitivity range around it's like minus 100 dBm or minus 90 dBm with respect to the LTE technology, or the NB-IoT means it's around minus 110 dBm. But in case of NTN technology, so it has to be like minus 135 or minus 140 dBm. The sensitivity range, that much of low level should be there, so the receiver can able to receive that signal and able to handle that and demodulate that particular signal. And the second test case is the maximum input level. So this is the maximum input level test case, is nothing but for example, there is a high power has been inputting to the particular receiver. Then how it is able to handle it. So these two test cases can be decide the dynamic range of the particular RX of that DUT. So these two test cases, if any designer of the NTN DUTs or UE designers will be keeping into the mind to evaluate these test cases. So that's why these TRX test cases are very much important with respect to the RF R&D or RF testing cases. Next. So this is the one more product for the NR NTN for RF testing. So the RF testing TRX measurements, again the product is MT8000A. So here also we are able to provide all the TRX test cases supported based on the release 38.521-5 release 18 release. So here delay and the Doppler shift. So here we will make it as a constant delay while simulating, and also NR NTN bands which is supported. Already the Bharat has been mentioned. So these are the different bands has been supported in the NR NTN. That is N254, 255 and N256. So current configuration, it is only supported for the SCA operation, that is called the standalone operation. The RX condition is the TRX two RX diversity. So one is that main RX and second is the diversity RX. So that's why we call it as a 2RX diversity. You know that why the diversity function is required, because one RX is always means we are not sure, because whenever the transmitter has been sending with different, we have that objects and so many hills. So the multi reflections has been coming at the arriving at the receiver end. So that's what the angle of arrival of the signal is always be not the same if suppose if you have the one RX, so due to that, so we can reduce that inter-symbol interference and all. So that's why we have to go for the RX diversity concept. So the satellite, the feasibility for this NGSO is the LEO. So LEO is the suggested for this currently for the NRNTN and all. So we are currently supported solution is the LEO orbit, low Earth orbit. Currently, this solution will be suitable for that one. Next. So these are the similar to like we have discussed, right? That NB-IoT, NTN 3GPP specifications for the TRX. Here also for NR-NTN, the spec 38.521- has been defined. These are the TX and RX, the same. So it is very important for any designer, even for the NR-NTN DUTs, has to be evaluated with these TX and RX test cases. It must pass all these test case specification as per the 3GPP. So let us discuss more on the what is the carrier leakage and in-band. Carrier leakage. You know that how much carrier has been deviated. So those test cases we can able to see, and occupied bandwidth. So we have allocated one particular bandwidth. Let us suppose 100 megahertz bandwidth we are allocated for the particular user. Then the channel bandwidth should not be varying while transmitted. So while transmitting through a air or anywhere, because so it has to be 100 megahertz or below that. It should not be, because of the spread or the interference to interference, co-channel interference or adjacent channel interference. Due to the interference, it should not be varying. So it has to be, allocated bandwidth. And also the spectrum emission mask. So this is called the in-band emissions, which we are measuring within the channel itself. So what is the in-band emissions we can able to measure? That is called the spectrum emission mask. When comes to the adjacent channel leakage ratio, this is also like, for example, one user we are allocating the one particular channel, then this channel it should not leakage higher powers interferences to the adjacent channel, because it is affecting the adjacent channel. Even this also has to be taken care while designing that what is the adjacent channel leakage ratio. This is the one of the important. These are the basic fundamental cases for any TX TX design in the TX design. Yeah, it is similar reference sensitivity and max input level cases which I already discussed. This is also same for even NR-NTN case also. Next. So these are the what is the current NTN market trend. If you talking about satellite network operators, if you see this is the roadmap for the satellite network operators. So currently 3GPP, based on the 3GPP for the NB-IoT case, the Skylo, which is currently they focused on the Geo and GSO. So we are also collaborated with the Skylo, and we have evaluated with them. We have successfully evaluated with the Skylo packages on the RF solution with MT8821C. We have achieved a Skylo of around sensitivity of around minus 138 dBm as a reference sensitivity level we have achieved with the Skylo. So similarly, if you see that for NB-IoT NTN, the 2026 Iridium is the next LEO in the plan and the pipeline. In the 2027, the Telesat is the one of the satellite network operator. When it comes to the NR-NTN, in the 2025, we have set the LEO based on the LEO lower Earth orbit. And also 2026, the Insamart and EchoStar and Ericsson are in the pipeline for the NR-NTN as well. So when it comes to the mobile network operators, so how the mobile network operators, the terrestrial network operators currently are collaborating with the satellite communication provider SCP. So if you see that the SpaceX is the Starlink has been collaborated with the T-Mobile and the KDDI and the SoftBank. Similarly, for the Global Star, which is collaborate with the Apple in order to send that any emergency messages and all. So the Apple has been collaborated with them. Similarly, other OneWeb is with the Orange and NTT Docomo mobile network operators, and the Skylo, SoftBank, and the Verizon. So these are the different mobile network operators has been tie up with the satellite communication providers. So this is how that current market trend